Hi all, this is Mr. Yeager for chemistry. I know it says honors chem there, don't worry. It's on level chemistry. They actually, honors chem does it the same way. Essentially, it's not a topic that they do any much larger than we do. But we are looking at colligative properties. We're actually going to look at electrolytes as well. This is a very conceptual part. We don't do any math. We used to with colligative properties, but we don't anymore. This is very much understanding certain properties that solutions have that we can change based on how much is dissolved. So here we go. So we have to first identify the idea of electrolytes versus non-electrolytes, because we are looking at the solutes and how many particles do dissolve. So an electrolyte is a substance, in the end, that does conduct electricity when it is dissolved in solution. That's because it does separate out into its ion forms. Okay, it separates out into its two ions. All right, so it's able to conduct electricity because it has those charged components. These will affect colligative properties more, or differently, it will be more, than non-electrolytes do because of the way that they do separate out. Okay, so electrolytes separate, and again, in a moment, colligative properties depend on how many total particles there are in a solution. So if I'm separating out the particles, that means I'm getting two particles instead of just one when it's dissolved. So we have two types of electrolytes. We have strong and weak. Okay, clearly strong electrolytes conduct electricity well, and they will pretty much completely dissociate in water. Okay, that just basically means dissolve, separate. Weak electrolytes, they do not conduct electricity well, and they include things like acids that do separate, but not completely. Some will, there's a certain number that do it, and then the solution doesn't like it anymore. So a non-electrolyte, again, is a substance that does not conduct electricity. And this will primarily be polar covalent compounds. And these compounds, while they dissolve, nothing splits up with them. Okay, they all stay as one particle still, instead of like an ion, which could be a sodium and a chlorine ion. A sugar particle will dissolve, but will stay as one entire sugar particle. It won't separate out into its atoms. So the big thing here is, how can we test this? We can test electrolytes very easily based on the idea of how well they can conduct electricity, which we have these devices. We don't have them, unfortunately, here at the school I'm at, but that will turn on a light bulb, and you can see that turn it on, and that just shows that you do need some sort of circuitry. You need a battery that's running, but they help complete the circuit. Okay, so you can see if it's a strong electrolyte, it turns on nicely. If it's a weak electrolyte, it'll do it a little bit. If it's a non-electrolyte, it won't light at all. So again, there are examples. Basically, any ionic compound will be a strong electrolyte. So if you got to remember that ionic compounds, metal and non-metal, they'll be strong. Certain acids will be strong. So something like hydrochloric acid or sulfuric acid. Weak electrolytes include water. Okay, water can conduct electricity, it just doesn't do it that well. And then you have other ones, acetic acid, which is vinegar, and ammonia. And then things like sugar, alcohols, and oil, they don't really dissociate, so they're non-electrolytes. So that leads us to our colligative properties. All right, I believe we're going through 4 of them. All right, so these are all physical properties, not chemical, physical properties of a solution that changes based on how much more solute you add to the solvent. And again, it depends only on the amount that you do actually dissolve. It depends only on the concentration of the solution, not the identity of the solute. So this is one of those wacky things where it doesn't matter what the compound is. If that compound separates into 2 parts, and then I get another compound and separates into 2 parts, both of them will change the colligative property equally, as long as it's equal concentrations of them. So some of the colligative properties that you need to know is, the first one actually tells you what it does. It's called vapor pressure lowering. All right, so when you add more solute, the solution will, and that dissolves out into parts, it will lower what's called the vapor pressure of the solvent. The vapor pressure is the amount of vapor that does exist right above the liquid. Okay, so if you dissolve more solute, you're going to decrease the amount of vapor that actually comes out of it. Okay, so more solute lowers the vapor pressure. It's in the name. All right, so that's what this is showing. Normal water would have lots of particles. If I add salt in there, now there's not as many particles above it. All right. We have what's called freezing point depression. Freezing point depression, again, is trying to tell you what it's doing. It's depressing the freezing point, meaning it's lowering the freezing point even more. So if I add more solute, the freezing point will decrease, meaning it will go below what it is, meaning it will be more difficult for you to freeze that substance. This is why you put brine and salt on the roads prior to any sort of rain or anything like that to prevent the solution from freezing. Okay? You can't put the salt on top of the ice. It's already frozen. It has to be dissolved into the liquid, which then will prevent it from freezing on the road. So that's what you can see here. Freezing point of water is 0 degrees, but if we add salt to it, in case of seawater, it's negative 1.8. It's not going to be dramatic. That's the big thing. But that could be a difference. It could take longer for it to eventually freeze. It does the opposite on the other end of the spectrum. It will elevate the boiling point. So it will be more difficult for you to boil it. All right. If you add salt, the boiling point of water goes from 100 to something like 102.5. Okay. So it increases the boiling point, meaning you have to heat it at a higher temperature for it to boil. This is why in cooking we do add salt and stuff to the solution so that we cook it at a higher temperature, which could possibly make it cook faster, or you just cook it at a higher temperature to make sure it's done well. So again, so far all the names are telling you what it does. Vapor pressure lowers, freezing point lowers, boiling point goes up. That's what you're going to need to remember. The last one, which finally doesn't tell you what it does, I mean, I guess it does in a way, is what's called osmotic pressure. This is the pressure to prevent basically motion of water from one side to the other side of the solution. Okay? So basically you have like pure water on one side and then salt water on the other side. If there's a barrier in between, you learned about this back in biology with, oh shoot, what is it? Basically the idea of the cells bursting or shriveling up. I'm blanking on the name right now. Hypertonic or hypotonic solutions. You were learning about osmotic pressure there occurring over the membrane of the cell. If we increase the amount of solute on one side compared to the other, it will increase the osmotic pressure that will occur into that solution. That's what this is saying. So I guess you could say if you add more, you increase osmotic pressure. So we should say osmotic pressure elevated. So what we basically have is, again, what affects the colligative properties is the concentration of the solution. Higher concentration, it creates larger effect. It does depend on whether it's electrolyte or non-electrolyte. Electrolytes will have a larger effect versus non-electrolyte because you will have more particles, therefore higher concentration. That is it. Thank you.